Hello, everyone. Okay, welcome back to our first lecture, I guess I'll call it. And this one is on the scientific method. So it should be a relatively short lecture, but I hope you enjoy it. So, if we're going to talk about science in general, we might start with Aristotle. Aristotle, and over here is a picture of Aristotle and his teacher, Plato. Now, if you take a close look at this photo, or I guess I should call it a painting, it's kind of interesting because what they're doing with their hands is not unintentional. Plato was this very metaphysical teacher. Um, basically, the way that he talked about the world was not very scientific or fact based. It was very opinionated and a very smart philosopher, but not what we would consider science. If you take a look at Aristotle, his hand is sort of pointing towards the ground. And that's because Aristotle was very driven toward fact and the natural world. He is one of the first philosophers that's going to be interested in the natural sciences. One of the quotes of Aristotle, very famous, is Plato is very dear to me, but facts are even more dear, or something like that. So he was very, very concerned with actual facts and not sort of these metaphysical, sort of pseudo explanations for why things occur. He speculated about many things that were found to be true, like maybe up to like 100 years ago. We found out, oh, Aristotle said this was true, and it actually is true. He was, however, incorrect about a number of things, but he was so smart and so intelligent, nobody really ever questioned him. And he didn't really ever do experiments. He wasn't really a scientist as much as he was a philosopher rooted in the natural sciences in the natural world. One of the things that's we'll talk about in a second is he said that if you took a large object, like think of a bowling ball and a golf ball, and drop them at the same time, well, of course the bowling ball will go faster. And that was just sort of accepted as fact for a long, long time. However, we know now that that's not the case, and we'll talk about who actually figured that out. Now let's talk about this next person, Abu Ali al-Hassan, and he is a Persian, and he lived in modern day Iraq. And he's the first person, this is many, many years ago, to develop what we would think of as the modern scientific method. He created words like hypothesis and theory, but he wasn't really a scientist in the sense that he didn't do any experiments. But the way in which he said science should happen is pretty much the modern day scientific method. That's not to discount Mr. AlHassan here. He was a great astronomer. He coined and named over 240 celestial bodies, and a great, great mathematician at the same time. But not really a scientist in the way that he wasn't a practicing experimental scientist. So that's really all I'm trying to get at there. The next person I want to talk about is Galileo Galilei, and he's an Italian scientist. And unlike Aristotle, he didn't want to just say things, he wanted to prove them in so much as he wanted to do experiments. He was able to prove that objects fell at the same rate regardless of their size. And the story is, now I'm not sure if it's a fact, it might be a story, it very well could be a fact. But it's very long ago, so it's hard to tell these things. But the story is that he went up to the Leaning Tower of Pisa, dropped two objects at the same time. One was bigger, one was smaller, and he proved that those objects would accelerate and reach the ground at the same time. Now, there's plenty of videos of people doing that to this day if you want to look that up. Really interesting, and Galileo is the first to really prove and do the scientific method. What is the scientific method? It's really what we're here to learn about today. Well, first you have to question. First you observe something, okay? You observe plants growing. Let's just say that. And you question it. But that question has to lie within the realm of science in order for it to be a scientific question. There's two questions that I pose here. Is the moon beautiful? And when is the next full moon? Now, one of these, it's probably pretty obvious to you, one of these is possible to be answered by the scientific method. The other is not, because it doesn't fall within the realm of science. You can't collect any data on it. The moon being beautiful is an opinion, of course. I think it is quite beautiful, but there's no scientific way in order to test how beautiful something is. When is the next full moon? You can certainly test that, and you could, and we have, you can date and make calendars based on the moon cycle. After you have a question and it is scientifically based, you can then make a hypothesis. Now, hypotheses are sometimes referred to as educated guesses, and it's okay to call them that if you want to talk simplistically, but most scientists don't really like the word guess because it's not really a guess. It's basically an outcome that you think is very distinctly possible, but you need evidence to support it. So it's sort of a guess, but it's not really a guess. Just the word guess in term is not exactly the right way to describe it. But basically, it's a statement that is testable. It has to be testable. You have to be able to get collecta that might either support or reject a hypothesis. Now, I want to point out something here. You never prove a hypothesis. Let's just go back to the theory of gravity, right? I told you that a hypothesis can become a theory once it's supported and supported and supported over many, many years, and all the data and all that points to it being basically true. It's supported and it basically becomes fact. Now, whatever percentage you want to say, I'll say 99.99999 to infinite nines percent chance that gravity is always going to work the same way. But because it's science, we always have to keep in mind that for some reason we could wake up one day. Well, I guess if gravity stopped working, we wouldn't really wake up. But we could wake up one day and these things that we hold to be scientific fact could be disproven. And so we say we never prove hypotheses, but we can support them very, very strongly. Once you state a hypothesis, you must conduct an experiment, or else it's just a meaningless statement. Let's say that we see plants growing, and we see that if it gets good light, it grows well. And so our hypothesis becomes increasing light intensity will increase plant growth. Now, if you see, there's two things here: increasing light intensity, increase plant growth. And that becomes our independent and dependent variables. So these are sometimes confusing to students, but the independent variable, I like to say it's the variable I manipulate. So the variable I and independent manipulate. And that's going to be light intensity, because we are going to be manipulating the light intensity. Some plants will get low light intensity, medium, and then high. And then the dependent variable, it's what you're measuring. What are we measuring? We're going to be measuring plant growth. And for this, it's the plant height, or you might want to say if it grows any flowers, or how many leaves, or how many, whatever you determine to be your dependent variable of plant growth, that is what you're measuring. That's the dependent variable. So independent variable, dependent variable, those are the two we've got so far. Then we have something called control variables. What are those? Well, basically, it's everything else that happens to these plants that has to stay the exact same. So these plants have to be in the same soil. They've got to be in the same type of pot. They've got to be in the same temperature. They've got to be getting the same amount of water. They've got to be being lit by the same type of light, right? They've got to be every other factor in this experiment has to be exactly the same. The only thing that can be different is your independent variable. And the independent variable in this case is light intensity. So everything else beside those are your control variables, okay? Because you're controlling them, you're making them the same. I know that these words can sometimes get confusing, but make sure you write them out, make sure you look them over, and try to understand what's going on. Okay, now, not to be confused with the control variables is the control group. This is the group that does not get manipulated by the independent variable. And so in our light experiment, one group of our plants is going to receive no light. The reason that you have a control group is to make sure that it's your independent variable that's actually causing any effects. If for some reason the plant that grew the best was the one that had no light, that might point out that your independent variable isn't all that important, or maybe it points to something completely different. But we always have to have a control group in which our independent variable, that group is not getting exposed to it. Okay. Then once we've done the experiment, we're going to have data. And normally you collect data in a data table, but it has to be made sense of graphically. If you collect a bunch of numbers and you show me it in a data table, it really doesn't mean a whole lot to me until you A, run some statistics on them, and then B, put them into a graph. Now, we're going to do a number of different types of graphs in this course, but they all pretty much work the same way, in which you put your independent variable on the y-axis, and that is the axis running right and left, or horizontal, and the dependent variable, what you measured, goes on the x-axis, which goes up and down. So for this graph, this is just how temperature changes over time. So time is the independent variable, temperature is the dependent, what we measured, and you can see that at whatever time this was the temperature. And this, you call this a line graph, where you put points on the graph and connect them with a smooth line. We'll do that. We'll do a scatter plot, where you just put points on the graph. We'll do bar graphs. All different types of graphs can be used. Sometimes graphs are better suited for certain amounts of data than others. Like some graphs, some data would be better suited in a, I don't know, bar graph than they are a line graph. And so I'll teach you about how we could realize what graphs are more better suited for the data than others. But we'll get to that. Once you've gotten your experiment done, you've gotten your data, and you put it into a graph, you make conclusions. Is your hypothesis supported or rejected? So if we saw that as we increase light intensity, our plants grew better, whatever metric of growing better that is, either they're taller, they have more fruits, they have more flowers, that would support our hypothesis. If we saw the opposite, it would probably reject our hypothesis, correct? So that's what we have to do. We have to form a conclusion. And then what the best thing to do is retest. You have to do this 2, 3, 4, 10, 100 times. Maybe not for something as simple as growing plants with more light, but for very cutting edge science, we don't just test once. We have to test many, many times, do many, many replicates. Once you do that, and if all of your results are coming back similar and your hypothesis is still supported, you then send it in for a peer review, which you write up a paper, you send it in for a peer review. Scientists, peers of yours will read it, make comments and suggestions. Once you change them and they're all found to be accepted, then you publish. And it is a scientist's obligation to publish their work so that the rest of the scientific community and the community at large can learn and benefit from your findings, of course. And you publish, by the way, you publish in what are called peer-reviewed primary journals, okay? And so it's not like publishing in some sort of magazine or publishing a book as much. These are journals in which many scientists will submit work on similar topics. Maybe it's microbiology or animal biology, or physics and whatnot, any sort of thing. There's different journals for each, and you publish them, and that is the most important part, really, of scientists that are in the faculty position. A lot of times their job requires them to publish a few times a year or a few times every year. And so with that, I'm going to leave it there. That's the scientific method. I hope you enjoyed this one, and I'll see you in the next one.